The pump room sits in half darkness. Outside, the sky is beginning to pale, not yet sunrise, but that colorless hour when objects start to separate from shadow. Inside, the air is cool and motionless. The overhead lamps have not been lit. The boiler down the hall is banked for the night, its pressure holding steady, but its fires reduced to embers. Against the east wall, mounted on a vertical pipe run, hangs a brass flow meter. It is a simple device, a dial face marked in gallons per minute, a needle resting at 0, and beneath the glass, the faint gleam of mechanical gears. The pipe it monitors is part of a closed condensate return system, water that has passed through heating coils and is meant to flow back toward the boiler. At this hour, nothing should be moving. The valves upstream are closed. The pump is idle. The system is static. And yet, as the first pale light touches the dial face, the needle begins to move. Not forward, backward. Slowly, steadily, it creeps counterclockwise across the dial. 1 tick, 2, 3. The gears inside the meter turn in reverse, registering flow in the opposite direction, as if water were flowing away from the boiler, uphill through a closed pipe, with no force to drive it. There is no sound, no vibration in the floorboards, no hiss of steam or gurgle of water, just the faint metallic whisper of the needle moving against its stops. Outside, the sky brightens. Inside, the meter continues its slow, impossible retreat. By the time the first worker arrives to light the lamps, the needle will have returned to 0. And no one, at first, will believe what they are about to see happen again the next morning. The foreman's name is Callahan. He has worked in steam systems for 15 years, long enough to know that meters do not lie, and long enough to distrust what he cannot explain. He arrives at the pump room just after 6 in the morning, as he does every day, carrying a lantern and a logbook. The room is still dim. The air smells of iron and coal dust and the faint sweetness of machine oil. He is halfway across the room when he sees it. The needle on the flow meter is moving. Not much, perhaps 2 gallons per minute, but definitely moving. And it is moving backward. He stops, sets the lantern on the floor, walks closer. The dial face is clear. The needle is retreating counterclockwise as if registering reverse flow through a system that should be completely still. Callahan places his hand on the pipe. It is cool to the touch. No vibration. He listens. No sound of water moving. He checks the upstream valve. Closed tight. He checks the downstream valve. Also closed. The pump motor is off. There is no explanation for flow in either direction, let alone reverse flow. And yet the meter insists. For 3 minutes he watches the needle creep backward. Then, as gradually as it began, the motion stops. The needle settles at 0. The room is silent again. He writes it down. Calls over 2 of the morning crew. They stand together and watch the next morning. Same time, same motion. The needle moves backward for several minutes, then stops. One of them suggests the meter is broken. Callahan shakes his head. If it were broken, it would behave erratically. This is precise, repeatable. The meter is working. It is the system that makes no sense. By the end of the week, the phenomenon has acquired a rhythm. Every morning between 6 and 6:15, the meter runs backward. Not violently, not suddenly. Just a slow, steady retreat of the needle across the dial, registering flow in the wrong direction through a closed, static pipe. The duration varies slightly, sometimes 2 minutes, sometimes 4, but the timing is consistent. Dawn, every dawn. The chief engineer is called in. His name is Mercer, and he has designed condensate systems for mills and factories across 3 states. He arrives on a cold Tuesday morning, just before sunrise, and stands in the pump room with his hands in his coat pockets. The workers stand behind him. No one speaks. The sky outside is just beginning to brighten. At 6:07, the needle begins to move. Mercer watches it for 30 seconds, then walks the length of the pipe run. He checks every joint, every valve, every connection. Everything is tight. Everything is cold. He listens at the pipe wall with his ear pressed to the iron. Nothing. He returns to the meter and watches the needle complete its slow backward arc. When it stops, he stands there for a long time, staring at the dial face. The next day, he orders the meter removed and replaced with a new instrument from a different manufacturer. The installation takes most of the afternoon. The new meter is calibrated, tested, and sealed. The following morning, the crew gathers again. At 6:09, the new meter begins to run backward. Same motion, same duration, same impossible reversal. Mercer writes a telegram to the meter manufacturer. The reply comes 2 days later. Instrument functioning as designed. Check system for backflow. But there is no backflow. There is no flow at all. The system is closed. The valves are shut. And yet, every morning at dawn, the meter registers motion where there should be none. A flow meter is a mechanical contract. It is built on the assumption that fluid will pass through it in one direction, driven by a pressure difference or a pump. Inside the casing, the moving fluid turns a rotor or a paddle wheel. The rotation is counted by gears, and the gears drive the needle on the dial face. The system is simple, reliable, and entirely dependent on one condition: that fluid is actually moving. In a closed condensate return system, flow should occur only when the pump is running. Water collects in a receiver tank after passing through heating coils. When the tank fills to a certain level, a float switch activates the pump and the water is pushed back toward the boiler. Between pumping cycles, the system is static. The water sits in the pipes. The pressure equalizes. Nothing moves. The meter in the pump room is installed on a vertical section of pipe between the receiver tank and the boiler return line. Its job is to measure how much water is being returned. During a pumping cycle, the needle should swing forward, registering flow. Between cycles, the needle should rest at zero. Under no circumstances should it move backward. There is no mechanism to reverse the flow. There is no pump downstream. There is no siphon. The pipe runs uphill from the meter to the boiler. Gravity cannot explain it. Pressure cannot explain it. The valves are closed. And yet every morning, the meter insists that water is flowing backward through the pipe. Not a lot, 2 or 3 gallons per minute at most, but enough to turn the rotor, engage the gears, and move the needle. If the meter is functioning correctly, then the fluid is moving. If the fluid is moving, then something in the system is generating flow. But what? The engineers gather the maintenance logs, the valve schedules, the temperature records. They begin looking for patterns. The first clue comes from the boiler operator. He mentions, almost offhand, that the reversal always happens after the night shift banks the fires, but before the day shift brings the boiler back up to full pressure. During that window, the system is cooling. Not rapidly, the cast iron holds heat for hours, but steadily. The water in the pipes, the metal of the pipes, the air trapped in the high points, all of them are losing temperature together. Mercer requests a thermometer. The next morning, he measures the temperature at 3 points along the pipe run, near the boiler return at the meter, and near the receiver tank. At 5:30, before the reversal begins, the temperatures are stable but not uniform. The pipe near the boiler is still warm from the previous day's operation. The pipe near the receiver tank is cooler. The section in between, where the meter is mounted, sits at an intermediate temperature. At 6 o'clock, he takes the measurements again. The temperature near the boiler has dropped slightly. The temperature near the tank has risen slightly. The section at the meter is changing fastest. He writes down the numbers, then watches the meter. At 6:08, the needle begins to move backward. He checks the thermometer again. The temperature at the meter is now nearly equal to the temperature upstream and downstream. The gradient is disappearing. He makes a note in his logbook. Reversal occurs during thermal equalization. He does not yet understand why, but the correlation is too precise to ignore. He also notices something else. When he taps on the pipe near the high points, he hears a hollow sound. Air-trapped pockets of air, compressed during the day when the system is hot and under pressure, now expanding as the system cools. He marks the locations. Later, he will calculate the volume. For now, he simply watches the needle complete its backward arc and return to zero. Mercer spreads the drawings across the table in the site office. The pipe run is 30 feet long, mostly vertical, with 2 elbows and a high point near the ceiling. He sketches the temperature profile at 5 in the morning, then at 6, then at 7. During the night, the warmest water settles near the boiler. The coolest water settles near the receiver tank. By dawn, the temperature difference creates a density difference. Warm water is lighter. Cool water is heavier. As the system cools, the density gradient begins to collapse. The warm water near the boiler cools and contracts, becoming denser. The cool water near the tank absorbs residual heat from the pipe walls and expands slightly, becoming less dense. For a brief period, these two effects overlap. The contracting water near the boiler creates a slight vacuum, not much, but enough to disturb the equilibrium. The expanding water near the tank, now marginally lighter, begins to rise. The system is closed. The water cannot simply circulate. It is constrained by valves, by geometry, by the weight of the column itself. Instead, something else happens. The trapped air pockets in the high points act as compressible cushions. As the water column contracts and expands, the air compresses and releases, creating a transient pressure wave. The wave propagates through the system, not as flow exactly, but as a slow, elastic displacement. The water shifts, just a few inches, just enough. And the meter, mounted in the middle of this shifting column, registers the motion. Its rotor turns. Its gears engage. Its needle moves backward, not because water is flowing in any sustained sense, but because the meter is sensitive enough to detect the momentary reversal of a fluid column adjusting to thermal equilibrium. The effect lasts only as long as the temperature gradient persists. Once the system reaches uniform temperature, the motion stops. The needle returns to zero. By the time the day crew lights the boiler, the system is stable again. Mercer writes up the explanation. He sends copies to the meter manufacturer, the factory superintendent, and 3 other engineers he respects. 2 of them write back. Both agree with his analysis. One suggests installing air vents at the high points to eliminate the cushioning effect. Mercer declines. The reversal, he notes, causes no harm. And it is, in its own way, a useful reminder that precision instruments will always reveal what careless observation misses. The meter was never broken. It was, from the beginning, functioning exactly as designed. What it recorded was real. A brief, transient reverse flow created by the interaction of thermal contraction, density gradients, trapped air pockets, and the elastic behavior of a closed fluid column during the transition from night to day. The sequence unfolds like this. During the night, the system cools unevenly. Water near the boiler retains more heat. Water near the receiver tank cools faster. By dawn, a temperature gradient exists along the length of the pipe. Warm water is less dense than cool water. Under normal circumstances, this would drive convection. The warm water would rise. The cool water would sink. But in a closed system with shut valves, convection cannot establish a steady flow. Instead, the system experiences a moment of adjustment. As the warmest section cools, the water contracts. Contraction reduces volume, creating a localized drop in pressure. At the same time, the cooler section absorbs residual heat from the pipe walls, causing slight expansion. The expansion increases volume and pressure. The two effects create a brief imbalance. Water shifts toward the lower pressure zone. The shift is small, a few inches of displacement at most, but it is real, and it moves in the direction opposite to normal flow. The trapped air pockets amplify the effect. Air is compressible. As the water column shifts, the air compresses and then rebounds, creating a pressure oscillation. The meter, mounted in the middle of the pipe run, registers this oscillation as flow. The rotor turns backward. The needle moves. For several minutes, the system is in flux, neither fully static nor fully flowing, but caught in a transient state as temperatures equalize. Once equilibrium is reached, the motion stops. The pressure balances. The air pockets stabilize. The needle returns to zero. The entire event is over in less than 5 minutes. To a casual observer, the system appears dead. No sound, no vibration, no visible change. But the meter knows better. It records what the eye cannot see. The slow, elastic breathing of a closed system as it adjusts to the light of dawn. The phenomenon is rare but not unique. Other engineers in other mills and factories have reported similar occurrences: meters that hiccup at startup, needles that drift during shutdown, instruments that register ghost flows in systems that should be still. In every case, the explanation is the same. The meter is not malfunctioning. The system is not leaking. What appears to be impossible is simply motion at a scale and duration that human intuition does not expect. Mercer leaves the meter in place. He adds a note to the logbook: reversal at dawn normal due to thermal equalization. No action required. The workers stop watching it. The foreman stops writing it down. But every morning, just after sunrise, the needle still makes its slow backward journey across the dial. And somewhere in the stillness of that pump room, the system breathes.